What's going on, guys? Today I'll be showing you how to run DeepSeek R1 14B, which is distilled from the Quen model. So this is essentially the best reasoning model that you can get from what I know, and as of March 2025, using the free T4 GPU with Google Colab. So this is definitely, sorry, let me just change that so that you can see my face. So this is definitely, the best you can get in terms of inference R1 compute. And as you can see here, if we compare 14B to O1 Mini, O1 Mini is slightly outdated, so this might not be a fair comparison. But anyways, you can see that it's on par, and O1 Mini is not a poor model in any sense of the word. So let's get into how we can deploy this. And I was going to show this really quickly so you can see what our RAM usage is. So we have 13.7 of the 15 gigabytes of VRAM, and also 3.1 out of the 12.7 gigabytes of CPU RAM. So there is auto offloading onto the CPU, since we do have 14 billion parameters, and we are using 4-bit quantization. So 4-bit quantization is just 1 byte. Or sorry, that's half a byte. So starting off, we have our independencies, so accelerate, bits and bytes, and transformers, which are all a part of the Hugging Face suite of LLM tools and APIs. And then from transformers, we need to get our tokenizer, of course, auto model for causal LM, which will load the model itself, which you can see right here. This is the model header or tag name. And then also bits and byte config, which will give us the quantization configuration. And that's the first thing we have here in the load model section. So in this, we have load in 4 bits equals to true. So 4 bits is half a byte, because 1 byte is 8 bits. So it's not even using, so if we just only load the model weights, it would be 7 gigabytes in VRAM. But you can see that we have a lot more than 7 gigabytes. And the reason for this is multiple. So first of all, when we're actually doing inference and computing on the weights themselves, we have to dequantize to float 16 to ensure numerical stability and accuracy. So this is adding overhead. And then there's a bunch of other things, such as 1 to 2 gigabytes, which is always used as a buffer by CUDA. So all this together is to say that even with 7 gigabytes of purely weights, we still have quite a bit more than that. So this is why, for example, we can do 8-bit, so just like 1 byte quantization here, because I've ran into just going over the CUDA memory. And you can see that this is most likely going to happen just by looking at the fact that when we use 4 bits, we're already at 13.7 out of 15, and we want to use the GPU mostly anyways. Okay, so I talked about loading 4-bit. Then the quant type NF4, this is one of the common ones that's used. I honestly don't look into this too much, but it's just like if you know BF16 and float 16. So one has a better dynamic range, but less precision, which is BF16, and then float 16 has a more fine-tuned precision, as much as float 32, but the dynamic range is less because the exponent, the mantissa, has less bits dedicated to it. So you can't represent the same size of number. I know that what I just said requires prerequisite knowledge. So all this is to say is that there's different ways of representing numbers in 4 bits, and NF4 is one of the most common. And then I already mentioned this. When we actually do compute, the data type that we're using is float 16. And once again, I kind of just took this because this is what the practitioners use. So there's not much rigorous theory behind these, but this is just the setup that we need to run our 14 gigabyte model. So 14 billion parameter model, not 14 gigabyte, or I think gigabyte is the same as billion, but anyways. Okay, so this is the model call here. So we load the model name, which is this, with our BNB, bits and bytes config here, and then device map auto. And once again, this is what decides where to allocate the weights in memory. And then we have a parameter here, which is whether or not to use cache. So I put it to true here, and this is to say that we are going to use more memory at inference to save on inference time computation. So that's to say it'll be faster. This is kind of like KV cache, but it's just caching the weights. And this is good because we'll be able to calculate our input faster, but you need to know that this might lead to going out of VRAM. And if that ever happens, just set this to false. So I've set it to true because empirically it has not gone over the limit. But if that does happen, that's the first thing that you can set to false. And then also we have our tokenizer here, which is just simply auto tokenizer. So everything's happening in the back end. The only thing that I wrote down here is that we need to put trust remote code equals true because the Quen tokenizer requires extant code from a remote repository. So just keep that in mind. And then this is what the actual run, the call looks like. So these are the 4 safe tensor packets of weights that are loaded onto our GPU. And this is, of course, quantized because if you see here, we have 8 plus 8 plus 8, and that's 24, but then add 2 for the 0.67s. So we're at 26, and then plus 3.5, so like around 25. And this is, this is kind of accurate because there should be around 28 gigabytes worth of weight since it's stored in a floating 0.16, a 2-byte format. So 2 bytes times 14 billion gives us around 28. And we're quantizing that though, because we don't have that much memory. And then we also load the tokenizer, which is only 7 million bytes or 7 megabytes. So that's nothing. Okay, So now let's go into our query model function here. So this is what takes in the user's messages. So rather the two messages. So there's the system, which is the chatbot itself, and then the user. That's why I have system and user input. There's a hyperparameter here, max new tokens, which you can play with. I'm sure that if you put this too high, then at some point you will run out of memory. So keep that in mind. And I will display what this actually looks like very shortly in terms of how it's interpreted by the LLM. Or let me just do that right now, actually. I think that's better. So when we go and put our system content, user content, this is how it looks like. So you have your helpful teacher, which is the system content. So this is just to say like what is the assistant actually doing, and then the user content would be, in this case, explain what death is to a 6-year-old. So that's what I chose here, and then the assistant follows up to respond. And then it's worth noting too that DeepSeek R1 and all of the reasoning models that DeepSeek makes use these think tags, which essentially encapsulates the reasoning process. And this was just done during the training because it's defining very strictly when the reasoning happens and when it ends, because it's kind of like an HTML tag. And let me see if I can find the end of the think. Yeah, there you go. So hold on. No, that's the beginning of the think. I'll get back to you on that, but essentially just know that think shows the start and end of reasoning. And this is what happens here. But the reason why we don't have this kind of JSON format and it's formatted in this special way with the angle brackets is because we have the apply chat template here. So apply chat template takes this universal way of modeling user chatbot interaction. So this format here works for like anything, Llama, ChatGPT, etc. But then every single LLM interprets this differently because it has a different tokenizer. So this apply chat template will take the message, and then we don't actually tokenize it because we have a tokenizer afterwards, but we do apply the template, which is this. So for DeepSeek R1, this is what the template looks like. I had something for Llama. So Llama has a different template. And if you want, you can search it up because it's interesting to know what the different models actually read in terms of the way that the chat is formatted. So we do say tokenize to false, or else we would tokenize it twice, which doesn't make any sense. And then add generation prompt equals true is just to say that this is the beginning of the dialogue. So this special token is added, begin of sentence, because of this parameter here. So if you put that to false, it would just start as you are a helpful teacher. So if it's not the start, then there's another one, I think it's called like continue conversation or something like that. And that's where you would use that parameter. Okay. And then we actually tokenize and we move it to the GPU because it needs to be on the same device as the weights. And then now we have our generate function, which is actually taking the inputs and outputting the next tokens, of course. So here we have, okay, max new tokens. I'll just start there first. So that's 200. And then we take from our input the input IDs. So this is what the tokenizer converts to. And this is how the model internally represents its tokens. And then the attention mask as well. What else is there? Then there's just the end of sentence token ID, which we want to be as the same as the tokenizer end of tokens ID, and the padding to be same as the padding tokenizer ID. This may not be necessary. I think by default it maps to this. So if somebody wants to actually ablate these and tell me what happens, then that would be good. Or I'll do this on my own after the video. And then we do we get our outputs, but then we need to decode our output since it's in the token, it's in the ID format. So if we just printed the outputs after this step, then it would just be like 132, 677, 32, which maybe means I am happy, but we don't know what that means as humans. And yeah, we need to decode that, and it's just in a batch way because we're using batches for parallelization. And then also skip special tokens equals to true. And this is another parameter that I kind of just accept. I haven't tried this as false, and I think that its default value is true. So once again, it's not really necessary to put that there. But let's now get to our examples to show that this really does work. So I'll just run this one more time to prove to you that does work, and we can just go to the next example. So the system is a grader of 8th grade students, and then there's 3 prompts here from decreasing or from worst to best in terms of the response of what is photosynthesis. Sorry. And here, once again, we can see the template that is applied. So we have the assistant and the user special tokens, and then we want to print it. So I'm not going to go through everything. You can go through it on the notebook on your own, but it essentially goes one by one through the students, and it starts thinking here, and then let's see when it stops thinking. And then it stops thinking here, and you can see this is by the backslash, which is the same as HTML. And then after thinking, it just gives the grades, so 3 out of 10, 5 out of 10, and 9 out of 10. And this is very interesting. I'll just say this right now. The last time I ran this, it actually gave 4 out of 10 and 6 out of 10 for these two. This one it always gave 9 out of 10. So it shows that it is stochastic, which is good. And now let's go back to our grading teacher. So, okay, it just worked. It just loaded in 20 seconds. That's pretty good. And yeah, let's see what it says. It's just thinking right now. I should also talk about remembering the person, maybe say that. So I think we ran out of tokens, and that's why it just stopped in the reasoning process. So we would need to increase our max token limit. But nevertheless, you can see that does work. And that's why you see here, I've actually set it to 1,000. So 5 times more than this one. And for that reason, it actually did get to the end of the answer. One thing that I have not been able to respond to yet, or like is puzzling me, so maybe somebody can find an answer for me, is that in the DeepSeek R1 training, it uses think, but then when it gives the answer, it uses answer. So I'll show you like what I mean. So if you just look here, there's like an answer. Oh, that's in the wrong place. So it's like answer and then backslash answer with the actual response. But for some reason, with this model, maybe it's because how the distillation happens, they just chose to remove that token, but it's not using it. Or actually, I think I may know the real answer. It's probably because we put skip special tokens equal to true. So putting that to false may or may not bring the answer token back, but that's kind of just a trivial thing. Otherwise, yeah, that's everything for the video. You can once again see that I'm very proud of this. I've like literally showed this like 10 times in the video, but it's very cool that we're within our RAM limit using the 14 billion parameter model, which is really good, honestly, as you can see by this table. And this video is inspired by another one I saw on YouTube, so I would like to give credit to that video. I just made this much more concise in the video, just removing a lot of redundant code. So that's why I wanted to make this video, and I hope you enjoy.